Hi, this is William from mathtuition88.com. Today we are going to discuss Fibonacci numbers and the golden ratio. The Fibonacci numbers are named after Leonardo Fibonacci, an Italian mathematician, and it is a sequence of numbers. Okay, some people will start with 0, or we can we can start with 0, 0, 1, 1, 2, 3, and 5. Now each number is the sum of the previous two numbers. So the first term we can write it as f subscript 0 is 0, f subscript 1 is 1, f subscript 2 is 1, f subscript 3 is 2, f subscript 4 is 3, and f subscript 5 is 5. Yeah, okay, that's correct. Okay, next, now we will discuss about the recurrence relation. Okay, so now there's this recurrence relation f n equals to f n minus 1 plus f n minus 2. This is the basic recurrence relation of the Fibonacci numbers. Okay, now if you think that I'm speaking too slow, you can adjust the speed. Adjust the speed to 2 times so that you can watch the video and finish at a faster rate. Okay, so how is this Fibonacci related to the golden ratio? They are actually related to the golden ratio, which we will write as this Greek symbol phi, which is actually root 1 plus root 5 over 2, which is approximately 1.61. So this is a very mysterious number. So we will actually show that the ratio of successive Fibonacci numbers actually converges to the golden ratio. Okay, the first person to actually observe this is actually Kepler. Yeah, Kepler is the famous mathematician and astronomer. Okay, so let me clear this. Okay, I clear this. Okay, now we'll continue with our discussion about the golden ratio. So now recall that we have this recurrence relation fn equals to fn minus 1 plus fn minus 2. Each term is the sum of the previous two terms. We will now divide throughout by fn minus 1. Okay, to get actually this. Okay, so first we will assume without proof that the ratio fn minus 2 over fn minus 1 converges. So this to be very rigorous, we actually have to prove it. But in this video, we will not actually prove it. So, okay, so now let's take a look at this equation which I circled down here. Okay, now we will take limits on both sides. Take limit means we will try to see what happens when n goes to infinity. So okay, taking limits will actually be the same thing, just that we put a limit notation down there. Okay, so this equation holds, and we will denote this fn over fn minus 1 as phi. So now we haven't said what is phi, this Greek symbol phi, but we will soon prove that it is the value that is very close to 1.6. We are getting there soon. So okay, now let me use green. This expression that I circle in green is actually phi. Okay, now upon greater thinking, we will see that this expression is also phi, because phi is the limit of the each term divided by the previous term, and this is also a term divided by, oh sorry, this is not phi, this is 1 over phi. Right, so because this is the reciprocal, this is the each term divided by the term after it. Right, so okay, we can put a side note now here. So the limit of fn minus 2 over fn minus 1 is 1 over the limit of fn minus 1 over fn minus 2, which is the same as 1 over the limit of fn over fn minus 1, which is 1 over phi. Okay, so now we have this nice equation down here, and we will multiply by phi on both sides to get phi squared equals to phi plus 1, and we will get a nice equation down here, phi squared minus phi minus 1 equals to 0. Okay, so we will save this equation because it's very crucial. Okay, the rest we will delete it to make up for some space. Okay, so please hang on because we are almost there. Okay, next let's see what can we do with this equation. This equation is a quadratic equation, so we can use the quadratic formula. Phi, the solution to this equation is minus b plus minus square root b squared minus 4ac over 2a, which, if you recall, is the quadratic formula. Okay, now we just sub in the b. b is minus 1, so now we have 1 plus minus root. Okay, b squared will be 1 minus 4 times 1 times minus 1 over 2 times 1, which will be 1 plus minus root. Okay, here is going to be 5 over 2. Okay, so so now there are two values, but we can see that phi is clearly positive because it is the ratio the limit of fn each Fibonacci term and the previous one, and all the Fibonacci numbers are positive. So hence we have that phi is 1 plus root 5 over 2. So this is the golden ratio, which as we mentioned earlier is approximately 1.6. Thanks for watching, and please subscribe to our channel. Thank you very much.